Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Jabri bin Azizi. My number make it B122410469. Today I'm going to present about digital signal processing, windowing filters, DER3373. For introduction, in digital signal processing, DSP, finite impulse response FIR, filters are widely used due to their stability and linear phase characteristic. One of the most common techniques for designing FIR filter is the windowing method. Direct extension causes spectral leakage, Gibbs phenomenon, or stop-band attenuation. Selected window and video overview. Selected window functions. Rectangular window, simple and easy to implement, best frequency resolution, high spectral leakage, and Gaussian window, smooth window shape, good side lobe suppression, and suitable for non-sensitive application. Rectangular window, theory and characteristic. Mathematical definition. The rectangular window is the most basic windowing function used in FIR filter design. It is defined as this equation and zero elsewhere. It means all samples inside the window are treated equally, with no wedding or smoothing at the edge. Time domain characteristic. In the time domain, the rectangular window has constant amplitude. As amplitude at the window boundaries, its shape looks like a simple rectangle, which causes sudden discontinuities at the start and end of the signal segment. Frequency domain characteristic. In the frequency domain, the rectangular window shows two important behaviors. Narrow main lobe provides very good frequency resolution. Closely spaced frequency can be clearly separated. High side lobes, negative 13 dB, causes strong spectral leakage, results in poor stop-band attenuation, which means unwanted frequency are not well suppressed. Trade-off. The rectangular window represents a clear trade-off. Best frequency resolution, narrow main lobe, worse leakage control, high side lobes, low stop-band attenuation. Because of this, the rectangular window is mainly used for basic FIR filters design demonstration situation where frequency resolution is more important than noise suppression.
Assalamualaikum and hi, my name is Muhammad Aizat bin Yamin with matrix number B122410476. So now I'm going to present about Gaussian window, theory and characteristic. In mathematical definition, the Gaussian window is a window function that is heavily used in signal processing because of its excellent ability to suppress spectral leakage. This window function has a shape based on the Gaussian distribution function, giving the window a bell shape. As you can see, the Gaussian window is defined. So the value of omega determines the width of the window, with larger values of resulting in wider and smoother windows, and smaller values of omega concentrating the windows around their centers. Time domain characteristics. In the time domain, the Gaussian window has a smooth bell-shaped curve. Unlike rectangular or triangular windows, it does not have sharp edges. This smooth tapering reduces abrupt change at the end at the signal boundaries, which helps minimize distortion in the frequency domain. After that, frequency domain characteristics. In the frequency domain, the Gaussian window exhibits the first one, wider main lobe. The signal energy spreads over a wider frequency range. Lower frequency resolution means harder to separate close frequencies. And second, very low or no side lobes. Almost no energy leaks into nearby frequencies, and it excellent leakage suppression. This means it does not create ripples in the spectrum. This removes side lobes but makes the main lobe wider. Trade-offs. The main trade-off of the Gaussian window is, first, poor frequency resolution due to the wide main lobe, and second, minimal spectral leakage because side lobes are extremely small or absent. Therefore, the Gaussian window is ideal when leakage suppression is more important than precise frequency separation, such as in noise analysis and spectral smoothing.
Assalamualaikum, my name is Faizal Akmal bin Mustafa Kamal. My shoot number is B122410424. Now, let's compare both windows side by side. This shows us the clear trade-off between them. In time domain, rectangular has flat, sharp edge. Gaussian has a smooth bell curve. In frequency domain, rectangular has a narrow main loop that's been good frequency resolution. Gaussian has a wider main loop, poorer resolution. But look at side loops. Rectangular has high side loop, about minus 13 decibels. Gaussian has very low side loops. This means rectangular causes lots of leakage. Gaussian causes very little leakage. So that the trade-off is rectangular gives the best resolution but worse leakage. Gaussian gives the best leakage control but poorer resolution. These visual plots make the trade-off immediately clear. On the left, the time domain comparison. The blue rectangular windows is completely flat. Every sample gets equal weight with abrupt cutoff at the edge. The red Gaussian windows show that characteristic bell curve smoothly tapering to zero. This smooth transition is why Gaussian minimizes artificial frequency components. In the middle, frequency domain on a linear scale. See how the blue rectangular peak is much narrower and sharper. This meant it can distinguish. In the middle, frequency domain on linear scale, see how the blue rectangular peak is much narrower and sharper. This means it can distinguish between two closely spaced frequencies better than any other window. The red Gaussian peak is wider and smoother. It spreads energy over a broader frequency range. Now, the crucial view, frequency domain on dB scale, the blue rectangular curve shows those high side loops peaking at about negative 13 decibels. This causes spectral leakage where signal energy spills into neighboring frequencies. The red Gaussian curve dropped rapidly to below negative 14 decibels, almost no side loop at all.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aziz Rifki bin Ibrahim. My metric number is B122410425. So before we dive into the filter, let's quickly walk through the design process shown in the flowchart. So it start by initializing the workspace, then set the common parameter like sampling frequency and the filter order. So next, it branches based on the filter type, that is low pass, high pass, or band pass. Each part set its own cutoff frequency or frequencies, normalize them to the Nyquist range. Then they design the filter using FIR1 with a window that is triangular. So finally, all paths converge to compute and plot the magnitude and phase responses. Now let's look at each filter response individually. So let's begin with the low pass filter designed using a rectangular window. This filter is intended to pass low frequencies and block high frequencies. So basically in our code, the cutoff frequency is set to the 300 Hz with sampling rate of 2000 Hz. So the Nyquist frequency is about 1000 Hz. So we're looking at the magnitude response, we see that the frequency from 0 up to about 300 Hz are passes with nearly 0 dB attenuation, meaning they come through unchanged. This is the passband. Just above 300 Hz, the response begins to drop sharply. The transition from the passband to stopband occurs over a narrow band, roughly about 80 Hz wide, which is the characteristic of the rectangular window. This gives us a very sharp cutoff, which is one of the advantages of this design. However, in the stopband, that is frequency above roughly 380 Hz, we observe significant oscillation or ripples. These fluctuations mean that the signal just beyond the cutoff are fully suppressed. They reduce, but not eliminated. For applications needing strong noise rejection, this could be a limitation. Now look at the phase response. In the passband, the phase is a straight line with a negative slope. This indicates linear phase behavior, which means all frequency in the passband experience the same time delay, especially 25 samples or 12.5 milliseconds. This preserves the shape of the input signal, which is highly desirable in audio and communication system. So in the stopband, the phase appears erratic, but that's expected because the signal magnitude is nearly zero. They're making a phase mathematically undefined. We simply ignore the region. So in summary, the rectangular window low pass filter gives a sharp transition and linear phases, but suffer from oscillation in the stopband that limit its ability to fully block unwanted frequencies. Now we consider the high pass filter, also built with a rectangular window and the same order. This filter does opposite. It blocks low frequencies below 300 Hz and passes higher frequency up to the Nyquist limit of 1000 Hz. In the magnitude plot, we see that the frequencies above approximately 380 Hz are passes with 0 dB gain. This is the pass band. The transition from stop band to pass band again spans about 80 Hz, starting near 300 Hz. This sharp transition is another hallmark of the rectangular window. Below 300 Hz lies the stop band. Here, instead of being flat, the response shows pronounced oscillation. This fluctuation means that low frequency component close to the cutoff like 250 Hz are attenuated, but not completely removed. So this limit filter effectiveness in rejecting, say, power line hum or DC drift. Turning the phase responses, we see a smooth linear decline across the passband from 380 Hz to 1000 Hz. This confirms the linear phase, all past frequencies are delayed equally by 25 sample or 12.5 milliseconds, ensuring no phase distortion of the signal waveform. As before, the phase become noisy in the stop band below 300 Hz, but this is not meaningful since those frequencies are suppressed. We disregard that part. In short, the high-pass rectangular filter offers a narrow transition band and excellent phase linearity, but its stop band performance is limited by oscillation near the cutoff. Finally, Let's examine the pass band filter, designed to pass only specific range of frequencies from 200 Hz to 600 Hz using the same rectangular window approach. This magnitude response show a clear pass band centered between roughly 280 Hz and 520 Hz. So where the gain is close to 0 dB, signals in this range will pass through large unchanged. On both sides, the filter transition into stop band below 200 Hz, the lowest stop band above, and the above is 600 Hz, the upper stop band. Each transition zone is about 80 Hz wide, consistent with the rectangular window behavior, and this gives us two sharp edges, one at the low end, one at the high end of the pass band. However, in both stop band, we again see strong oscillation where it's a very low frequency or very high ones. Neither is fully suppressed. The fluctuation peaks around negative 13 dB, meaning out of band signal close to 200 or 600 Hz can still leak through significantly. Now, the phase response within the pass band 200 to 600 Hz, the phase is a straight line with consistent negative slope. This confirms linear phase. All frequencies in the pass band are delayed by the same amount, 25 samples or 12.5 milliseconds. This is crucial for maintaining waveform integrity in applications like biomedical, sensing, or audio processing. So outside the pass band, both below 200 Hz and above 600 Hz, the phase plot becomes jagged and unstable. But again, since the magnitude is near zero, this phase behavior has no practical impact and can be ignored. To conclude, the rectangular window and pass band filter provide sharp band edges and linear phase within the pass band, but exhibit oscillations in both stop bands that reduce its ability to fully reject unwanted frequencies. So each of these filter, low pass, high pass, and band pass demonstrate the classic behavior of rectangular window FIR design. Sharp transition and linear phase, but with oscillation in the stop band that limit their suppression capability. While useful for learning and certain real-time application, more robust design often requires smoother window like humming or Kaiser.
Hello and Assalamualaikum. My name is Farid Akinai bin Zulkifli. Number metric is B122410437. Now I want to present designing flowchart using Gaussian window. Okay, first is start, the process begin. And second is initialize, clear the WordPress, clear variable and close open window. And third is set common parameter, define the sampling frequency and the filter order. And four is select filter type, choose the type of filter to design, low pass, high pass or band pass. And five is set cutoff for low pass, high pass and band pass. And number six is calculate normalized frequency. C is for low pass, high pass and band pass. And number seven is design the filter using Gaussian window. And this code for low pass, high pass and band pass. Number eight is compute frequency response and the focus like this. And after that is calculate magnitude 20 log 10 ABSH. And calculate phase is like this coding. And after that is plot magnitude and phase response. Display the filter frequency and phase response. And after that end the process finishing. Okay, that is coding for low pass using Gaussian window. And first is filter equation. Sampling frequency is 2k Hz and cutoff frequency is 300 Hz. For filter order is 15. For normalist, cutoff frequency is D is for coding. Design FR low pass filter using coding this is this. And four is compute frequency response. And number five, plot magnitude and phase response. Okay, next is result for magnitude response and phase response of low pass FR filter using Gaussian window. For magnitude, the filter pass frequency from 0 Hz up to approximately 300 Hz with minimal detonation. Here is the pass band of the filter around 300 Hz to 400 Hz. The magnitude drop sharply, indicating the transition band wave frequency start to be attenuated. Above approximately 400 Hz, the magnitude is significantly attenuated, indicating the stop band of the filter. The ripple in the stop band, a characteristic of FIR filter. For phase from 0 Hz to approximately 300 Hz, the phase response is approximately linear, indicating a constant group delay in the pass band. Above 300 Hz, the phase response becomes nonlinear with some discontinuities, especially in the stop band. Next is coding for high pass using Gaussian window. OS filter specification. Sampling frequency is 2k Hz and cutoff frequency is 300 Hz. For filter order 15. Second, normally for our frequency, them like low pass, and for design paper high pass filter using Gaussian window, it is coding for high pass using Gaussian window. After that is compute frequency, and number 4 is spot magnitude and force response frequency. Okay, next is result for magnitude response and phase response for high pass APR filter using Gaussian window. For magnitude, the filter attenuated frequency from 0 Hz up to approximately 250 Hz. Significantly, this is the stop band of the filter. The ripple in the stop band, a characteristic of FAR filter. Around 200 Hz to 300 Hz, the magnitude rise sharply and indicated the transition band where frequency start to be passed. Above approximately 300 Hz, the magnitude is close to 0 dB, indicating that this frequency pass with the minimal attenuation. It is the passband of the filter. For phase from approximately 300 Hz upward, the phase response is approximately linear, indicating a constant group delay in the passband. Below 300 Hz, the phase response becomes nonlinear with some discontinuity, especially in the stop band. Next is coding for bandpass using Gaussian window. It is slide, but for design FI bandpass filter using Gaussian window, encoding is like this. Next is result for magnitude response and phase response for bandpass FR filter using Gaussian window. For magnitude, the filter attenuates frequency from 0 Hz up to approximately 200 Hz significantly. This is the lower stop band of the filter, the ripple characteristic of FAR filters. From approximately 200 Hz to 300 Hz, the magnitude rise, indicating the lowest transition band. The filter pass frequency from approximately 300 Hz to 700 Hz with minimal attenuation. This is the pass band of the filter. From approximately 700 Hz to 800 Hz, the magnitude drop, indicating the upper transition band. Above approximately 800 Hz, the magnitude is significantly attenuated. This is the upper stop band of the filter. For pass from approximately 300 Hz to 700 Hz, the phase response is approximately linear, indicating a constant group delay in the passband. Outside the passband, the pass response becomes non-linear with some discontinuity, especially in the stop band. This is all for me. I pass to my friend. Thank you.
The theoretical difference we just saw translates directly to practical engineering choice. Different application demand different window characteristics. Let's explore where each window provides optimal performance. First, rectangular windows. Despite their leakage issue, they have specific valuable applications. Basic anti-aliasing pre-filtering. In simple data acquisition system like low-cost sensor network and or basic ADC interface, rectangular windows provide adequate performance with minimal complexity. When stop band rejection is not critical but cost and simplicity are prioritized, rectangular is the pragmatic choice. Transient signal analysis. When analyzing impact sounds, mechanical shocks, or electrical transient, we need to preserve sharp time domain features. Rectangular windows maintain abrupt signal edge that would be smoothed out by other windows. Think of testing material strength with hammer impact. We need to see the exact impact timing clearly. Theoretical and education use. Most importantly, rectangular windows are foundational for DSP education. Every engineer learns about spectral leakage and the Gibbs phenomenon first with rectangular windows because they clearly demonstrate these fundamental concepts. They serve as the baseline against which all other windows are compared. Now, for Gaussian windows, this is where they enable sophisticated, high-performance application. Radar and sonar path shaping. In radar system, Gaussian windows are essential. They minimize range side loops, false echo that could mask real targets. Without proper windowing, a weak drone signal near a strong aircraft return could be completely missed. Gaussian windows provide the clean target separation needed for reliable detection. Time frequency analysis in audio processing, music analysis, and speech recognition. Gaussian windows enable clean spectrogram through the Gabor transform. They minimize cross-term interference that can create artificial frequency components. Bird research use this to analyze bird songs. Audio engineer use it to analyze instrument harmonics. Medical signal processing. In EEG and ECG analysis, strong signal components should not leak into neighboring frequency bands. Gaussian windows ensure clean spectra for accurate diagnosis. In sleep studies, they help distinguish different brain wave patterns without artificial frequency spreading. This radar simulation illustrates why window choice matters critically. The blue rectangular window create these pronounced side loops around the main target. Notice how they rise nearly as high as the actual weak targets. In a real radar system, these side loops could completely mask nearby aircraft or weather phenomena. The red Gaussian windows suppress these side loops dramatically. All three targets, one strong, two weak, remain clearly distinguishable. The weak targets are buried in noise or side loop interference. Let me put in practical terms. In weather radar, this could mean distinguishing light rain next to a developing thunderstorm. In military radar, this could mean detecting a small drone flying near a commercial airline. In automotive radar, this could mean reliably identifying pedestrians near vehicles. The Gaussian window smooth time domain taper directly enable this clean frequency domain separation. This is not just theoretical, it's why modern radar systems standardize on Gaussian or Gaussian light window for pulse shaping.
In conclusion, various windowing functions are associated with different trade-offs regarding the performance of finite impulse response FIR filters. A rectangular window has strong frequency resolution along with high spectral leakage. On the other hand, a Gaussian window has strong leakage separation with low frequency resolution. It is therefore important to consider design preference, namely resolution or spectral purity, depending on which is of more importance to a particular application. Thank you.